Good evening. My name is Hunter, and this is content review for general chemistry students. Week 4 is covering chapter 10, liquids and solids. Talking about intermolecular forces first, what is the evidence that all neutral atoms and molecules exert attractive forces on each other? This one should be fairly obvious. The fact that we can experience matter in a variety of states is pretty strong evidence for this. So, all atoms and molecules will condense into a liquid or solid in which the attractive forces exceed the kinetic energy of the molecules. And there's a footnote here at sufficiently low temperature. So define the following and give examples of each. Starting with dispersion forces. Dispersion forces occur in between all atoms, um, and it's the result of as an atom develops a temporary dipole moment, which is when an electron is distributed asymmetrically around that nucleus. Remember that the way that we think about where an atom is located is a series of probabilities. We're kind of moving away from the orbital model, but it still works, right? As that electron is traveling around that space, its negative charge, the negative charge associated with it, is also moving around that molecule. So dispersion force. Let's see. And a simple way to think about this could be in terms of magnets, right? You have positive and negative ends. Negative is attracted to positive. Now, a dipole-dipole attraction is a much more scaled up version of this kind of attraction. Um, Before I get too far ahead of myself, a good example of a dispersion force would be any monatomic element, such as argon. Yeah, we'll leave it at that. So dipole-dipole is the textbook example is that north and south pole battery, or not batteries, magnets sort of lined up to each other, where this is an attractive force that results from that electrostatic attraction of the positive end of one polar molecule with the negative end of another polar molecule. Excuse me. Um, Iodochlor iodine monochloride is the example. An example. There are many. Result of electrostatic attraction between positive and negative poles of a molecule. And finally, hydrogen bonding. Hydrogen bonding is my favorite. And an easy way to remember this is hydrogen likes to have fun, F-O-N. Fluorine, oxygen, and nitrogen are species that like to participate in hydrogen bonding. Hydrogen bonds form whenever a hydrogen atom is bonded to one of these more electronegative atoms. Um, the electrostatic attraction between the partially positive hydrogen on one molecule and the partially negative atom on another molecule gives rise to these really strong dipole-dipole interactions um, called hydrogen bonds. And this phenomenon is um, responsible for the unique properties of water and its role in supporting life on Earth. So you have partial positive and partial negative associated with each of these poles. The water molecule itself has a polarity sort of in this direction. Arrow points towards the negative, and then the little plus sign at the top here is your positive region around the molecule. Okay, that's hydrogen bonding. I kind of like this week because it's a little less math heavy. It's much less math heavy. It's more concept driven, which I think is very um, I don't know, shows that you have a good sort of rational understanding of the content. So the types of intermolecular forces in a substance are identical, whether it's a solid, a liquid, or a gas. So the forces that we just described uh, carry through regardless of state. So why then does a substance change phase from a gas to a liquid or a solid? We kind of hinted at this. Well, not hinted at this. This is the definition, right? If we're looking at kinetic energy compared to the intermolecular forces, right? If the intermolecular forces exceed the kinetic energy, we're going to have a solid. Remember that temperature is simply a measure of the average kinetic energy um, of a substance, right? So very, very low temperatures, lower kinetic energy. Those atoms aren't vibrating too much. Very, very high kinetic energy. I'm going to draw just an arrow over this way, increasing kinetic energy. If kinetic energy is just less than or equal to the intermolecular forces, we're going to have a liquid. And I say just less than because we want the molecules to slip past each other, but they still have some attraction. And if kinetic energy far exceeds the intermolecular forces, we're going to have a gas. Cool. Yeah. So as kinetic energy increases, molecules vibrate away from each other. We get these phase changes. As intermolecular forces, attractive forces increase, we have movement in the other direction. So temperature is a really easy one, but there are other ways to manipulate this, and we'll get a little bit deeper into um, atmospheric pressure in particular and how that interacts. Okay. Neon and hydrogen fluoride have approximately the same molecular masses. Explain why the boiling points of neon and hydrogen fluoride differ. So we have neon, which is our noble gas, monatomic, likes to hang out by itself. Its octet is full, not super electronegative, wants to hang out by itself. The only IMFs it's participating in are dispersion forces. Hydrogen fluoride, by comparison, has an extremely electronegative atom. Fluorine is the most electronegative atom with a very positive Excuse me, I drew that backwards. So we have this very, very strong dipole. Fluorine is also one of those species that will participate in hydrogen bonding, which is our strongest. Our strongest IMF. Moving away from that discussion a little bit, compare the change in the boiling points of neon, argon, krypton, and xenon with the change of boiling points for hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide, and explain the difference between the changes with increasing atomic or molecular masses. I've taken the liberty of recording the boiling points and the molecular masses for each of these. And the trend that you should notice, let me pull up my periodic table here. Yeah. Neon, argon, krypton, xenon were going down the period. And the same is true for these strong acids that we have assembled here. Hydrogen fluoride, fluoride being the most electronegative species, highest on the period, and working our way down. So these are in order, and you will notice that our boiling points, with the exception of hydrogen fluoride, are increasing as we go down this period. The same is also true for our noble gases. So BP increases down the period. Group. Um, so that's your general trend, right? Our molecular masses are also increasing. Xenon is heavier than krypton, is heavier than argon, is heavier than neon, and therefore has a higher boiling point. We could look simply at the mass and intuit this heavier thing, this more massive atom requires more energy to displace it. I think that makes sense, right? Hydrogen fluoride is unique because it's participating in hydrogen bonding while the rest of these are not. So dipole versus H bonding. We have increased mass as we go down, but we also have increased polarizability. And polarizability is the tendency of the electrons, and actually, let me just look up the definition so that I don't get that wrong. It's the tendency of one atom to be influenced by the other. I think it's the electron specifically, but I want to be totally sure here. Show me polarizability. It's not going to show me. All right, fine. Polarizability refers to the tendency of molecules to generate induced electric dipole moments when subjected to an electric field. So yes, it's the tendency of the electrons to influence each other between species. Okay. Let me get back to my notes here. Okay. I notice I'm actually getting a little ahead of myself. That's more to do with question 24. which is asking about surface tension and viscosity. This should also be fairly intuitive, I think. The surface tension and viscosity values for diethyl ether, acetone, ethanol, and ethylene glycol are shown here. We have these nice little ball and stick diagrams of each of them with their molecular formulas over here, followed by surface tension and viscosity. So surface tension, um, getting ahead of myself again, explain their differences in viscosity in terms of the size and shape of their molecules and their intermolecular forces. So viscosity is resistance to flow, right? Honey is very, very viscous. Diethyl ether is not viscous at all. It's a very, very low viscosity value. So it wants to flow very easily. And when you get to work with this in the lab, you'll see that it's a very, very thin liquid. It also evaporates very, very quickly, which is part of this. So in terms of the size, this is a very large molecule. Interesting. It appears to be. It appears to be a very large molecule. And we don't have we don't seem to have any hydrogen bonding going on. There is an oxygen there, which is pretty electronegative. This molecule is not very polar, right? We have del positive, del positive. I would call that a nonpolar molecule, right? The trend that they want you to see here is that larger molecules and larger contact areas corresponds with greater polarizability as well. So that greater polarizability, that great contact patch, and actually I can probably, so that we don't have to just visualize this, you could see, that's interesting, how two of these might be inclined to nest together, right? They have that really big contact patch. That increased contact patch, but also that larger molecule is more polarizable, means that it's going to have less surface tension and lower viscosity, I guess. Yeah, so that's kind of the trend. Large, large molecules, large contact patch. Relates to increased polarizability. Scroll, please. Okay. The same trend is true for surface tension. That should be apparent. Um, surface tension, remember, is the force required to expand the surface area of a liquid. So it forms this kind of skin, right? If you've ever filled a glass up too full, you'll remember that you can see the water will bulge over the surface of your glass. Um, and you have specific practices that you're supposed to follow in lab for measuring, is it at the bottom? Um, I am forgetting the vocab word for that, but it's the bottom or the top of the, why can't I remember? And anyway, whether that is convex or concave on the surface of your graduated cylinder depends on whether the adhesion or cohesion forces of that particular liquid are greater, which is related. So for 27, the surface tension and viscosity of water at several different temperatures are given in this table. As temperature increases, what happens to the surface tension of the water? Explain why this occurs in terms of molecular interactions and the effect of changing temperature. Just like we were talking about earlier, increasing the temperature increases the average kinetic energy of the substance. And so there's more energy in the system. Those molecules are more likely to slip past each other. So that is reducing the surface tension uh, of the water. And similarly, making it less resistant to flow. As temperature increases, what happens to the viscosity? Makes it less resistant to flow. And this is occurring because that increase in average kinetic energy is overcoming some of those intermolecular forces that are holding those water molecules together. Cool. So now we're getting into phase diagrams. From the phase diagram for water, which I've copied and pasted below, determine the state of water at 35 degrees Celsius and 85 kilopascals. We've got temperature on our x-axis, pressure on our y-axis. We have this black line, which diverges for this particular substance. Excuse you. And you'll note that this is not drawn to scale, so this is kind of wobbly. We're going to make some informed guesses. So at 35 Celsius, which is not, oh goodness. Let me set this to background really quick. So if halfway is 50, 35 is somewhere around there. And 85, so if we're going to say that, that's 85. We're somewhere in here. That's inside the water or liquid phase. We'll just do L. Negative 15 and 40. So here's 0. Negative, we don't even have any units on there. And 40 is somewhere around here, but that should be solidly in the solid ice phase. Solid, thank you. Negative 15 and 0.1 kilopascals. So negative 15, we'll just say that that's like way out here, and 0.1. We should still be in solid ice. But if this isn't drawn to scale, if pressure is sufficiently low, actually, at 0.1 kilopascals, maybe that's like right here, and negative 15 is somewhere here, we could have water vapor. So I'm going to write solid slash gas. 75, it's right about there, and 3 kilopascals. This is another close one. I'm going to go ahead and say gas. And finally, we've got 2 more. 40, so not quite halfway, and 0.1, extremely low. We're going to be in the gas phase. 60 degrees Celsius and 50. Ooh. These not being drawn to scale is a real bummer. That's 50. That would be 75. 50 kilopascals. I'm going to say liquid. So hopefully when you have to answer these questions, you have a phase diagram with a little bit more resolution than what I have right now. so that you can find those relationships. When you're at the triple point, that is when you have equal quantities of water cycling between solid, liquid, and gas simultaneously, which is kind of cool. All right, pressure cookers. We are going to do a little bit of math now. Pressure cookers allow food to cook faster because the higher pressure inside the pressure cooker increases the boiling temperature of water. A particular pressure cooker has a safety valve that is set to vent steam if the pressure exceeds 3.4 atmosphere. What is the approximate maximum temperature that can be reached inside this pressure cooker, and explain your reasoning? I was talking about average kinetic energy and phase changes. Boiling in particular is related to atmospheric pressure. So if we have liquid water at room temperature and we put it in a container and pull the atmosphere out of it so that it is less than 1 atmosphere, less than ambient atmosphere, the water will boil even though it is safe to touch. And that is the result of the decrease in pressure relieving those intermolecular forces, and the kinetic energy, the latent kinetic energy is sufficient to allow those molecules to hop around and boil. So I'm laboring that point because, well, it's related to the ideal gas law that we were talking about last week. So we're given this equation, which is ln P2 over P1 equals delta H vapor, which is the enthalpy of vaporization. And this will be a tabulated value over R. And R in this case is 8.314 joules over mole dot Kelvin. The enthalpy of vaporization of water is 39.67 kilojoules per mole. We have a P2 value. This is the pressure that that the pressure cooker is set to vent at. So this is the maximum pressure inside our pressure cooker. P1 is simply going to be 1 atmosphere. So that's going to simplify our equation a little bit. Finally, we have temperature 1. We know what temperature 1 is because it's the boiling point of water. We know that we're dealing with boiling water inside of this pressure cooker. So that is 100 degrees Celsius plus 273 Kelvin. Temperature 2 is what we're solving for. So now we could just plug these into this equation. I'm actually going to move this a little bit, give myself more room. But you'll notice that we need to get T2 by itself. And this was really confusing for me, even though it should just be like pretty straightforward algebra. But I'm going to go ahead and show you guys all the steps to get there. So we have, let me do this in black, keep it consistent. Multiply both sides by R, P2 over P1 equals delta H of vaporization, T1 minus T2. Now, divide both sides by the enthalpy of vaporization. We're trying to get T2 by itself. We're going to subtract both sides by T1. Gives us R ln quantity P2 over P1 delta H vape minus 1 over T1 equals negative 1 over T2. We're almost there. To get the reciprocal, we can simply multiply both sides, not multiply, raise each to the negative 1 exponent. This allows us to just plug in our values here. So our new equation is R ln P2 over P1 delta H vape minus 1 over T1 to the negative 1 power equals negative T2. We can simply multiply by negative 1. Gives us a positive value for T2. And now we plug in our values. And you should get a value of 412.458 Kelvin, or 139 degrees Celsius. I want to draw your attention to the difference in, that's not what I wanted to happen. I want to draw your attention to the difference in units here. When you enter that delta H of vaporization, you need to convert it to joules per mole. Otherwise, you are going to get a much smaller value than you were expecting. Okay. More phase diagrams. Determine the phase changes that carbon dioxide undergoes as pressure is increased at a constant temperature. And I've written those temperatures off to the right here. So constant, let's see, pressure increased at a constant temperature. So if we're starting at negative 50, start right here, we will start in the gas phase, move into the liquid phase, and finally into solid phase. If we start at positive 50, we can only go from the gas phase to the supercritical fluid phase. Negative 40, similar story, gas to liquid to solid. And at positive 20, should be right here. I'm going to eyeball that and say it's right there. So we'll definitely have a gas phase. We will definitely have a liquid phase. We might have a solid phase as we increase pressure at a constant temperature. Cool. Is it possible to liquefy nitrogen at room temperature, which is about 25 degrees Celsius? Is it possible to liquefy sulfur dioxide at room temperature? Explain your answers. We're talking about supercritical fluids. Or supercritical substances. I went and found some phase diagrams for nitrogen, which is on the left, and for sulfur dioxide, which is on the right. So for liquid nitrogen, not liquid nitrogen, to liquefy nitrogen at room temperature, let's find, so halfway would be 50, half of that is 25. We're in a gas phase. There's no way to have a liquid phase. at room temperature for liquid nitrogen. At room temp. Not possible. For sulfur dioxide at 25 Celsius, we hit the critical point and we have some supercritical region. It seems possible that we could have liquid sulfur dioxide at room temperature at the appropriate pressure. But we may also have some substance going into that supercritical region. So I'm going to put possible, maybe. All right, that's everything I have for you. If you haven't taken them already, good luck on your midterms. Take care of yourself this weekend. Do find time to rest. It was a gorgeous day. I'm a little bummed I wasn't outside for more of it. I look forward to seeing you all next week. You can find these recordings on the PSU Learning Center YouTube channel. As always, email me if you have any questions. See you next week.